Hello, everyone. I think we can get started. Welcome to another weekly webinar presented by DB Sales and Service. This week, we are presenting solar heating technology. The presentation will be given by Suni from Enerworks. My name is Austin Buckles. I'm the sales manager at DB Sales. If you do have any questions, of course, during the meeting, please, submit those questions in the questions and answers windows. We will either answer them live, or we'll wait until the end to answer more questions as we continue on. But with that, I'll hand the presentation over to Suni so we can get started. Thank you very much.
Hello, everyone. Can everyone see the screen?
Yes.
Okay. All right, as Austin mentioned, my name is Suni Ball. I'm the general manager for Enerworks. I have George Fonseca with me here, who's our in-house designer, to answer any questions. And essentially what we're going to go over is the design and uses for solar thermal. So we're based in Woodstock, Ontario, which for anyone that knows Canada is actually kind of the in between Buffalo and Detroit if you were to take a shortcut through from Michigan to New York. And we used to focus a little more heavily on residential. More lately, it's commercial systems. And we also manufacture the Enersol unglazed solar pool heater, which has been extremely popular this year with all the shutdowns. So some typical uses for solar heat is obviously swimming pool and domestic water. Domestic water would be kind of the first thought. You can use it for space heating, but it's better to have an alternate load in the summer, like a swimming pool. We've used it for a solar air conditioning project. And then you can use it for industrial and commercial heat. So dairy farming and milk processing for sanitation is just one example that we'll go over. One of the things that I often have to explain to people is everybody seems to have the most efficient collector. I think that's probably not true, but obviously they want to promote their products. In general, an unglazed collector, those are the mats that you see on a roof. Those are the ones that are going to heat your pool. They don't have any glass and they don't have any insulation. So they call those unglazed collectors. That's the green line represented on the far left. So what this is just giving you a representation is how efficient these products are. So if you look at the inlet temperature versus the ambient temperature, typically pool collectors would be very low because you're not trying to heat it up to anything, say, above 85, 86 degrees. Your ambient temperature is often, in some cases, warmer than that. So, but as your ambient temperature gets further and further away from the temperature being collected at the collector, you can see the efficiency drops pretty dramatically. So you would never be able to heat domestic water or space heating with an unglazed panel. Then you have flat plate collectors. So flat plate collectors are the ones that look like skylights in most cases. They're often confused with photovoltaic collectors for electricity. They tend to be most efficient and most popular with residential domestic hot water systems, particularly the further south you go. So they do have a glass cover on them and they do have some insulation on the back. But as you can see, the higher the temperature you go, the less efficient they become. And then the last one is vacuum tubes. And keep in mind, these are representations only. There's more and less efficient in each category. Vacuum tubes tend to start out a bit lower, but have a relatively flat efficiency curve. So they're ideal for collecting temperatures as high as 180, 190 degrees because they don't lose as much energy as other products. So I'm going to get into some things you need to think about when you're designing or considering solar hot water or solar thermal systems for any type of design. The first one is stagnation, and one of our German engineers that we deal with explained this very well to me. He said, consider it a boiler that you can't shut off and you can't control the temperature, and design everything else around it, and it'll last for 25 years. So stagnation is essentially when the system overheats. So this could be because a pump failed. In domestic water systems, it could be as simple as the city shutting water off to the building. It could be a loss of electricity. There's a number of different systems or reasons why this would happen. And if you've oversized the system, stagnation can occur when you've heated up the domestic water tank. So for instance, as hotels were shutting down recently, even though all the equipment's working, stagnation can occur because there's not enough load in the building. So unglazed collectors, meaning the pool collectors, generally are not affected by stagnation. And the example I'll give is a garden hose on your lawn. At some point, the heat being absorbed is admitted. There's an equilibrium, and so it'll only ever get so hot before it goes back out. But where you have collectors that keep the heat in, that are designed to keep the heat in, they can get quite hot. So a vacuum tube system, our system has a temperature limitation in it, but you could see temperatures in excess of 300 degrees. But you won't feel it because the vacuum is such a good insulator. But you do have to design around it. So a lot of people's first choice to go to control temperature is what I'll call active stagnation control. And this is something that you're actually familiar with for air conditioning systems, chillers, which is a type of cooling system. So a dry cooler would be something to maintain temperature below a certain level. But the one challenge, and I've used these in projects, the challenge you have is if your dry cooler fails, or if the pump in the system fails, or you lose electricity, you don't have any active at that point because it's no longer working. So we've had simple things like a valve, like an automatic valve, stop working. And if you're planning for power failures, now you have to add in a backup generator. And so it ends up becoming very expensive to provide the redundancy if you're trying to use this as your primary method of overheat protection. How we design for overheat protection, I mentioned the vacuum tube collector that we use is actually made in Germany. I think it might be one of the only ones made outside of China these days. But it, in addition to the temperature limitation built into the collector, and that limitation is, it doesn't matter, you could let it sit all year, overheat every day, it does not, it won't break. But we also designed the system to purge the collector from your solar fluid. So what happens is the water and glycol solution, we pressurize the system so that it'll boil at about 230 degrees. And what the water boils just before the glycol, what happens is it creates a small amount of steam, pushes the fluid out of the collector. We use an oversized expansion tank, and the half a gallon per collector is actually absorbed in the expansion tank. When the system cools, it just recombines, and there isn't any damage to the collectors, the system, or the glycol. The glycol is really what you're trying to maintain the life of. So we tested this and overheated a system for 440 days in a row, and found when we sent the sample back to Germany from the manufacturer of the glycol, their response was there was no significant difference from this product or a new product as far as corrosion protection, which is the key in a lot of these systems, and freeze protection for any systems that might see temperatures could be exposed to freezing conditions. And the other advantage of doing this is it keeps your system fairly low pressure. So, some of these systems are only pressurized to 25, 30 PSI. The taller the building is, the higher you have to pressurize it. But it allows you to keep the design with a much lower pressure in the system. This works in the event of a power failure, a load disruption, or a mechanical failure. And in some cases, that mechanical failure might be as simple as animals chewing on, like we've had squirrels chew on sensor cables. And so your temperature sensor is no longer reading correctly. So this is a really, I would say, simple but effective way to prevent damage to the system. And it's something that we've used for 15 years, but it's been used extensively in Europe for probably twice as long as that. How our vacuum tube works, there's actually two vacuums. So if you take a look at the first picture on the left, the blue absorber is actually inside a glass tube. There is a vacuum in the glass tube. That vacuum is designed to prevent heat from escaping through the glass. Glass is a great transmitter of thermal energy. And so the vacuum is a perfect insulator. It doesn't allow much, if any, of that heat to leave. The second is there is a vacuum in the copper tube that goes into the manifold. And why you want that is the fluid will actually start to boil at a much lower temperature than the boiling point typically. So you can actually have this fluid boil, let's say starting at 100 degrees. And what happens is that vapor travels up to the condenser at the top. You've got fluid in your collector manifold passing by. It cools the fluid, and it's essentially like a rainfall cycle where it evaporates, condenses, evaporates, condenses. And that's how your vacuum tube system would work. Now, what happens with our stagnation method is the clever people in Germany designed it with a fluid and a vacuum that allows it to create a vapor lock if, for instance, you have no load. So if the temperature in the manifold gets to, it was 165 Celsius, which is, I think, about 350 degrees, at that point, you have a vapor lock. So it won't actually get any hotter than that, and essentially it stops producing energy. And this is the reason. There is another company on the market that makes an overheat protection in the condenser, but it's a mechanical device, and the mechanical device can actually get jammed or wear out over time. This is a nice solution because it can't wear out. It's essentially built into the design. The mount angles on a vacuum tube can go as low as 20 degrees, as high as 90. Anything above 70, you really limit how much energy you're collecting. So while you can put it on a wall, you significantly decrease the amount of energy that you can collect. Unless you're trying to do space heating, you're actually trying to shed some of that, I guess, the more summer sun. And I'm just noticing here that I've made a mistake. So it's 320 is the temperature limitation feature. And because the glycol we use has a temperature of breaking, like a breakdown temperature of 338, you don't actually have any concern about it damaging the glycol, which isn't the case for a lot of standard heat transfer fluids. Collector location and orientation. So south to southwest is actually kind of ideal for collector locations in most areas for North America. In a lot of cases, latitude. But as you can see here, you have a pretty wide swath of, kind of east to west, as well as up and down, like as far as the angle of the collector goes. So, if you're off the latitude by 5% or 10%, like you're not losing a tremendous amount of energy. And that's partially because solar thermal collectors are so efficient to begin with, that like 2% difference in this doesn't really have an overall impact on your system. Whereas if a photovoltaic collector is generating at 17% efficiency, a 2% reduction at that point is actually a fairly significant decrease in the overall output. So it's a little more critical for photovoltaics to have the ideal tilt and orientation. In the event that you're not able to get a south-facing, say 35-degree angle, there is some leeway with the solar thermal collector that you may not have with some other technologies. The balance of the system, and this is something that we'll talk about a little bit later. So the pump station and controls. So this is our pump station controls. We used to make one that was very, very large, called it the piano. And in light of shrinking mechanical rooms and just the cost of having larger mechanical rooms, we came up with a pump station that is is more compact. And this is pressure tested, pre-wired, and essentially can fit through a standard doorway. And all you're doing is plugging it into a standard 120-volt outlet and connecting your temperature sensor on the collector and temperature sensor in the tank. It has a bypass loop in it. So on a system, let's say you have a 4-story building, you could have a few hundred feet of piping. That piping would actually be ambient temperature. So it could be a little bit cooler in the winter months or even overnight. And if the pump were to start up, then it would actually start to siphon heat potentially from the tank. So this pump station will actually bypass the heat transfer heat exchanger until the loop temperature is warmed up sufficiently. Then it will close and direct it through the heat exchanger to add that heat to the storage tank. So why that's important is because the system will sometimes stop and start during a cloudy day. You don't necessarily need to bypass that, but particularly as you go further north in California, you could have just above freezing temperatures in the loop, or even below freezing. You don't want the heat exchanger exposed to that. Even if you don't have freeze protection concerns, you don't really want to heat a tank up and then siphon the heat out. So having the bypass loop does two things there. It increases your overall system efficiency and adds an extra layer of protection. So this has your PRVs, check valves, and it has a digital pressure and a digital flow meter built into it that you can read from the control. Storage tanks is another, very important one. I'm actually going to go back. There's been a number of systems, and we can talk about this later. A number of systems where the design of the pump station has been put outside on the roof. And I just want to be clear, I'm not aware of any manufacturer that makes the pump station to go on the roof exposed. Ours is actually designed to be in a conditioned space. The limitation here is actually the controller on the front of the unit. It can't go below freezing, and it can't go above 100 degrees. And a doghouse on the roof will actually see temperatures that exceed that, particularly because the pumps and the piping itself can be very hot. And so it's just something to think about when you're designing. There is the possibility to separate components, but that should be thought about earlier on in the process. This particular unit's roughly 2 feet by 2 feet by about 4 feet tall. Storage tank, so this is really important. This is your battery. So if you're generating electricity and you want to store it, you use batteries. Our battery is essentially hot water, nice inexpensive solution. And essentially you're going to match the storage tank to the load that you're trying to save for the day. So for instance, if you have a 900-gallon load and you want to save roughly 35%, you're going to want to be able to store at least 300 gallons of fluid and size your system accordingly. And so at a certain point, it makes more sense to go with the larger tanks. Some companies will opt for the smaller tank. The system on the right, you can see they had to use 16 tanks because it was a basement of an apartment where the tank was going. So they didn't have an option to use a larger tank there. The one on the left is actually an outdoor application with a horizontal tank. So it's just something to consider. I know in California, the seismic requirements are often such that you have to have a horizontal tank. So it's important to identify that early on. And the weight of the tank can also be a problem on the roof. So it's something to make sure to bring up. The piping is fairly significant. So one thing to consider, the piping itself can go from whatever the ambient temperature is to 180, 190 degrees within a matter of an hour. So there is expansion and contraction in the loop. And you're going to want to make sure when you insulate the loop that it does have some type of protection, not just UV protection, but a lot of times animals like to pick away at the rubberized insulation. In some cases, the piping can be about a quarter of the system cost. So When you can avoid long piping runs, not only does it save money on the project, but it makes the system more efficient because the longer the piping run, the larger the heat loss is in the piping. Um, some collectors, like older designs of collectors, use a higher flow rate. Our collectors use a lower flow rate, so we're rated just about half a gallon per collector per minute. And so it's a relatively low flow rate, and we're trying to generate a very high return temperature. And by doing that, we can actually reduce the flow rates and the piping significantly in a solar hot water system. This is just an example of Armaflex type of insulation. I don't know if it was Armaflex or K-Flex, it doesn't really matter. In some cases, they'll actually suggest you can paint it and that looks protective, but you can see this one, I think, was about 4 years after it was installed. And what happens is people step over it, like you see in the corner there, and they clip it with their feet, their work boots. But even the parts that weren't disrupted, you can see where the paint is actually starting to crack, and that insulation is going to lose its effectiveness. Balance of system. So in a lot of areas in California, you're not going to have to worry about freeze protection, but in some cases you are. The bigger challenge is actually corrosion protection. So this system, like the fluid, can last 5 to 6 years, possibly up to 10 years. So you don't need to continually refill it, or there's no chemical feed pot on this. It's a self-contained system that's made to last for a very long time with the correct heat transfer fluid. And so it does two things. It provides your freeze protection, but it also provides the corrosion protection in a system. And it's really, really important that you don't use just any heat transfer fluid, because a lot of heat transfer fluids that are designed for building heating systems are nowhere near capable of maintaining temperature swings that you're going to see in a solar hot water system. Add to that, with the steam back stagnation system, that separation of the water and the fluid from your inhibitors will often allow those to precipitate out on the pipes, and it'll actually coat them and reduce your overall efficiency. This is an example of a typical system. So most systems are going to be simple preheat systems, where the water goes, domestic water goes into the tank, and then we're drawing from the tank and just recirculating through the solar system. We're going to heat the tank up to whatever temperature we can get. So sometimes we'll be able to heat it up to 140, sometimes to 160. Some days, if it's cloudy, we might only add 20 degrees to the tank. So if the incoming water temperature is 60, we might only get it up to 80. But any energy we add to that is energy that your conventional heater, whether it's electric or gas, it doesn't have to heat up. So you're saving that energy every day, regardless of the amount. And this also simplifies controls. There's no need for complicated controls, because it's a simple inline pass-through system that we heat up what we can. It passes through to the conventional system. And you always want the fresh cold water for your solar system. If you remember the chart that I showed you from the beginning, regardless of the type of system you're using, they all perform the best if you're using the coldest water. So you want the temperature of the water not to get too hot right away. You can use a higher temperature, like we've done systems where you'll add the heat to a hot water recirc loop. In those cases, you can only use a vacuum tube system, because the temperature of the loop is already so hot that you won't add any heat to it. But in general, you want to, for a simple domestic water system, you want to preheat that water coming in. So identifying some of the projects, if you have a higher daytime use, higher summer use, is it a constant predictable load? We're going to talk a little bit more about some of the information that we require that's different than what you might size, say faucets or a conventional water heater on. So solar works on an average daily load. So, I think ASHRAE might actually have some standards for this. whereas your hot water system is often designed for your peak load. Solar is designed for the average. So if you take that average and say it's 1,000 gallons a day, it might be higher one day, lower the next, but the average is say 1,000. Then we're going to look at what the solar fraction is. And the solar fraction is just essentially the percentage of solar heat that you can provide to your average daily load. So some people will play with those numbers to get that solar fraction, because if you've got 1,000 gallons and you need 30%, you have to heat up 300 gallons. But if you only have 500 gallons average load, then you only need to heat up 150 gallons. So it really does depend on what that starting average daily load is. And we're looking at the design of the system. And then in addition to that, the roof space that's available and the mechanical room space that's available. We had started one project where they actually wanted to put in twice as many collectors, but in that particular case, there wasn't enough room for the storage tank. And without enough storage, the system will just overheat and shut down for the day. So you really need to balance the collectors, the load, and the storage together. In other cases, you've got room for storage, but not enough room for collectors. So you need to resize the storage to match the collectors. And the type of building is important. If it's a building that has a commercial pool that you're heating, that's a very constant load. But if it's a dormitory, there might not be any load in the summer. If it's, in Canada, we've got ice skating arenas when they were open. And so they're only going to be open in the winter. So it's really important to know what the load profile of the building is, because there are some cases where solar thermal may not be the best choice for that type of application. So most collectors that you're going to use are certified through the ICC SRCC rating. Over here is where I tend to design to, so it's category D, full sun. Some people will use category C, particularly with flat plate collectors, because there's a big difference. The higher the temperature you go, the less efficient the collector is. So you can see that warm, water heating in a warm climate, the collector itself will produce 52,600 BTUs per day on average. But in a space heating or water heating in a cool climate, it's 44,900 BTUs per day. Now, I tend to use category D in California because it's somewhere in between the commercial hot water heating and warm water heating. Commercial water heating is always a higher temperature application than domestic hot water for residential systems. And I found this to be very close to any simulations that I've seen. So I typically would use the 44,900 BTUs per day. In some cases, we go to the other, but this is where if you're comparing collectors, and this is the other thing. So these collectors are 50, I think they're 50 or 55 square feet. A lot of other collectors are only going to be around 28 square feet. So it's really important to look at the total output of the collector, not just the number of collectors. So if you're looking at a 100 collector flat plate system, the square footage and the performance might be such that you could actually reduce the overall number of collectors, but the square footage itself might remain the same. And on this sheet just below here, it'll actually tell you the square footage in addition to the sheet. So this is where I'm going to give you some examples of installations. This is a flat plate collector that we used to manufacture. We don't manufacture these anymore, but this is an example of a flat roof with I think it's called a sleeper curb. This is an example of a corrugated metal roof where you're flush mounting to the roof itself. This is in South Carolina. Now, one thing I want to point out, and you'll see some in other pictures, is this is actually two 30-tube collectors. When they're connected, you can't actually tell that they're not just one large collector. So aesthetically, they look really nice. The way they design them is that the tube distance from tube to tube on the collector is the same distance from the tube distance of the first collector to the second collector. So it makes for a fairly seamless design. When you put them together, it looks like one large collector. We used to sell more of these direct flows. These you can actually rotate sideways. They don't have the overheat protection built into them, and as that came out, we gradually moved to this one. But what you're seeing here is banks of 60 tubes, like 3 20-tube collectors, and you can see again that they're aesthetically they look fairly nice just because it looks like one large collector. This is again, hotels or retirement homes are actually a pretty good opportunity for solar heating. Larger residential is an opportunity. This particular house has 120 tubes, so 2 banks of 3 collectors, and that heats the pool, a large amount of domestic hot water, the hot tub, and in the winter, just to the right of that is the garage. It's a 3-car garage, and if there's any extra heat, then we add that heat to the garage in the winter. So that's a fairly significant load. You probably won't find a standard domestic hot water heating system is going to be very economical for most people because the price of natural gas is fairly inexpensive. But where you have large energy demands, like a pool, the hot tub, or large amounts of domestic hot water, I think this one here has, they heat up like almost 200 gallons a day of hot water. You'll find that that's kind of the threshold where it might make a little more sense to put solar hot water in. This is a retirement home that's actually just down the street from us. So this is the application we did for solar cooling. And these collectors generate temperatures up to 195 degrees. They're run through an absorption chiller, and we were able to permanently remove the electric chilled capacity in the summer. And in the winter months, there's a pool there. We add the heat to the building heating loop, domestic water, and the pool. So we were able to shave off, I think it was 70,000 kilowatts of electricity used for the chillers, and in the winter shave their natural gas consumption pretty significantly. And this is a nice load because in the summer we've got the absorption chiller, so we can add that heat in the winter, so it's a fairly balanced load. This community here was done, I'm going to say about 11 years ago now. So this is in Alberta, southern Alberta, just south of Calgary. And it does 52 homes. On the garage, the way they designed it, the garages are all in the back, and there's like a back alley to park in. And there's 800 4x8 collectors. And what they're doing is actually, it's a district heating system. So they collect that energy, and up in the top right corner of the picture, the borehole system, the building is here. So they go down, I think it's about 150 feet into the ground, and they're actually charging the earth with the heat from the solar collectors over the summer months. And then in the winter, they pull that heat out, and they won an award about 3 years ago because they were actually able to attain 100% solar heating for these 52 or 54 homes. And in addition to that, there's domestic hot water systems on each of the homes. That's a fairly unique application. So if you go to Drake Landing Solar Community, there's a website, it's dlsc.ca. You can actually take a look at how it's operating today, for instance, and what their milestones are this year. So while there's a lot of different technologies for solar or thermal, our focus is just thermal. So we tend to want to pick the right technology for the application. We have, a fairly deep experience across many different applications, and I think we're well suited to be a long-term partner for any developments in the solar thermal market. That's it for me.
Okay, thank you very much. Thank you very much, Suni. Yeah, I guess we have a question right here from Andrew Rauman just came in. I'll just read it out loud and see if we can answer for him. Keeping in mind the current trend to heat pump water heating, how do you think solar thermal compares to PV running a heat pump?
So I'm not as familiar with the options that you have for heat pump solar water heating, or like a water heating. I know for residential applications where your water heater is typically located in the garage, I know it can be a really effective solution. On a commercial basis, you have to understand, like, if it's located inside in a conditioned space, it's actually stealing, essentially the conditioned air from that room to cool the condenser. So in northern climates, it's not existent. Nobody uses it because it has limitations on the temperature that it can achieve. But it does work in a lot of areas where it's like a heat pump pool heater would work. But it is a slightly slower recovery. You're limited to the size of the systems that you can use at this point. And if it's in a mechanical room that's going to be warm, it's going to struggle to maintain that. An air conditioner or heat pump works off of leveraging, ambient temperature. So where your ambient temperature is too high, you end up losing the multiplication factor that you normally get out of an air conditioner or a heat pump. But that's not to say that they aren't good technologies. Certainly those in certain applications could be the right choice for it.
Okay, I think Andrew just said thanks, and so I think that answered his question. Thank you very much, Suni, for presenting today. I don't know if I mentioned it before, but all of our webinars that we do on a weekly basis are available on our YouTube channel that can be accessed, of course, going directly to YouTube or going through our website, which is dbsales.net. But again, if you do have any questions, feel free to reach out to me. Send questions to this particular email address, dbsalesca@dbsales.net, or call our office number. We again do these webinars every week. Next week will be a presentation from IntelliHot on how to go tankless in commercial buildings. So please RSVP to that. Invitations should be sending out at the end of this week. With that, thank you again for attending and have a good rest of your week.
Thanks again, everyone.
Thank you, Suni.